Hi there. This is a presentation on dimensional analysis, otherwise known as conversions, where we'll be using mass, moles, and molar mass. And toward the end, we will even use Avogadro's number, which can be seen on this awesome little tearaway advertisement at the bottom of the slide. Hope you enjoy the cartoons. There are a set of notes that accompany this slideshow that are linked on our agenda. And then also, please feel that you can pause at any time to try the problems yourself or to re-watch any of the problems. Let's start off with atomic mass. The average mass of an atom, of an element, is that atom's atomic mass. And we measure this in atomic mass units, which is abbreviated AMU, and sometimes with the symbol mu, it looks similar to a U. 1 AMU is exactly 1/12 the mass of an atom of carbon-12, which is a specific isotope. And an AMU is approximately the same mass of a proton or a neutron, and you'll remember from 8th grade science that that is in the center of an atom or within its nucleus. So they don't weigh very much. The average atomic mass of elements are listed in most periodic tables, and as seen in the example below, there are blocks from the periodic table for oxygen, sodium, and iron. And so oxygen, whose element number is 8, or its atomic number is 8, its average atomic mass is 15.999 AMUs. Sodium, atomic number 11, has a mass of nearly 23 atomic mass units, and iron, atomic number 26, has a mass of about 55.9 atomic mass units. If you were going to try to find the mass of one molecule or a formula unit, so the molecular or ionic compound, we would call it its formula mass. And we would need to then add up all of the atomic masses of the atoms within that compound by looking at the periodic table. Here is a block from the periodic table for the element carbon, whose average atomic mass has been highlighted in red. If you are looking at these slides that are linked on our agenda, you'll find that the periodic table takes you to a website called ptable.com. That's ptable.com, and it will look like this. And it's actually a really nice periodic table where every block is interactive and you can learn more about each of the elements. Later on, we'll talk about why the elements have been organized as they have, but they are very intentionally organized into rows and columns based on specific properties. For now, I'd like you to pay attention to the top number, which is the atomic number, the symbol and the name, of course, and then finally at the bottom is the average atomic mass of that element. So how can we use the average atomic mass? Well, if we wanted to find, say, the formula mass of a compound like ammonium nitrate, then we would use the information from the average atomic masses on the periodic table. And it's a really simple process. Students usually get this just fine. So let me do an example for you, and then you'll find on your notes that there are blanks for some of the other ones for you to try yourself. So first, I would consider my nitrogen. And if I look carefully, I'll see that I actually have 2 nitrogens in this compound. And so I would multiply 2 times the atomic mass of nitrogen, which from the little block that I've pasted over to the right is 14.007. So when I multiply that, I get 28.014 atomic mass units. Next, let's do hydrogen. There are 4 of them. Notice the subscript. The subscript applies to the element that it follows. So there are 4 hydrogens in this compound. So 4 times the atomic mass of hydrogen, which is 1.008, gives me 4.032 atomic mass units. And then lastly, we have oxygen. And as you can tell by the subscript, there are 3 of them, so 3 times 15.999 gives me 47.997 atomic mass units. So all I've done so far is added up the relative mass that each of the atoms contributes, or each of the elements contributes, but finally what we need to do is add them all up to find the atomic mass of the whole compound. And so then we would add these subtotals, the 28 plus the 4 plus the 48, and that gives us 80.043 atomic mass units. So let's try another one, and I think it would be a good idea for you to go ahead and pause and try to do this yourself for copper phosphate. Go ahead and pause now, and I will go ahead and keep talking about the problem. So for copper, we can see that we have 3 of those atoms of copper. And so I would multiply 3 by the 63.5. And then when we get into the parentheses, this is a little bit trickier, but basically you can think of the parentheses as containing a particular group of elements. And then any subscript outside of those parentheses applies to everything inside, and it's a multiplier. So even though the P does not have a subscript, we would assume that there is a 1 here. So 2 times 1 would give us 2. So that means that we would have 2 phosphates. That gives us 2 times 30.974. And then in this case for the oxygen, we have 8 of them. Because this PO4 is a specific type of grouping of elements, and the 2 implies that we have 2 of those groups. So we would need to have 8 oxygens for a larger mass of 127.92. And then like we did on the previous problem, we would add all of that up to give us a number of about 380.578 atomic mass units. So this is really great for measuring the mass of individual formula units or molecules, but it's really theoretical, and we can't see atoms and we can't see molecules. In real life, we measure quantities in grams, much, much larger samples. So we need to move away from atomic mass units and use a unit that is really based on reality and something we can literally get our hands on. So from there, what we do is we go to moles. A mole is exactly the number of particles in exactly 12 grams of carbon-12. That might not mean a whole lot to you, but it's basically a standard from which was used to make the definition of a mole. 12 atomic mass units is also the exact mass of 1 atom of carbon-12, and this is not by coincidence. This isotope of carbon-12, one atom of it has been designated to weigh 12 atomic mass units, and so from there, 1 mole of this particular same isotope has been defined as weighing 12 grams. And so it's important to note this number right here. This is Avogadro's number. 1 mole of any substance will contain 6.022 times 10 to the 23rd units. Now that units could be atoms, it could be molecules, it could be golf balls, it doesn't matter. It's just a counting number, much like is a dozen. So 1 mole of any substance is said to contain 6.022 times 10 to the 23rd units. And as you might recall from the How Big is a Mole video, this is really huge. And basically what we'd be doing is we would take this decimal and we would move it to the right 23 times, which would be off the screen. And that's a huge number. So the formula mass or atomic mass of a substance that's measured in atomic mass units is the same number as the mass of a mole of that substance in grams. So for example, if we have said that carbon weighs 12 atomic mass units, if we were considering 1 atom of it, well, if we had 1 mole of carbon, it would also weigh 12 grams. So all we're doing is we're switching the units, but using the same numbers. So this is pretty handy. Let's take a look at that on the next slide. Molar mass. The molar mass is the mass of 1 mole of a substance measured in grams, and we can abbreviate this as 2 capital M's, meaning molar mass. And so on the periodic table, there's really a dual purpose for that atomic mass. So let's check this out. Let's consider iron. We know that the atomic mass is 55.845 atomic mass units. That means that 1 single atom of iron, if you could even achieve that, would weigh 55.845 atomic mass units. However, if we had 1 mole of iron, meaning we had 6.022 times 10 to the 23rd pieces of that atom, pieces of that metal or atoms of it, it would weigh 55.845 grams. So 1 mole of iron weighs 55.845 grams. So notice the change in the units. Instead of saying 1 atom has a certain mass, we're saying 1 mole has a certain mass in grams. And we could see this most definitely. And approximately 1 gram is equal to a Skittle. So this would weigh about the same amount as 55 or 56 Skittles. Let's take a look at compounds. The same is true here. Let's consider water. It's a compound we're very familiar with. If we looked at the atomic mass for oxygen and hydrogen, we would add those up. For 2 hydrogens plus 1 oxygen would give us 18.015 atomic mass units if we had basically 1 molecule of water, but we can't really get at 1 molecule of water. However, we could have 1 mole of water. In other words, we would have 6.022 times 10 to the 23rd molecules of water, and it would weigh 18.015 grams. So we'll be using this number shortly. Let's take a look at some of the problems on the next slide. So let's use molar mass in dimensional analysis problems, in other words, conversions. So let's start with an example. If you were to find the mass of 0.35 moles of water, here's how you would set that up. We're going to need to reference our periodic table, so I've grabbed the hydrogen and oxygen blocks here for us. And we know we're definitely going to need to find the molar mass of water. And so all we would do there is, much like we practiced in the beginning, we know that we have two atoms of hydrogen for every water molecule. We multiply it by its its mass, and then 1 atom of oxygen at 16 is its mass, and you add all that up. But instead of saying atomic mass units, we want to say grams per mole, because we want to know how much does 1 mole of water weigh. So this is the preferred way to set up these conversion problems or dimensional analysis. Always begin with what you've been given, which in this case is 0.35 moles of water. If you like, you could write a 1 in the bottom bracket. It's unnecessary, but you could do that if you don't like having a kind of an open bottom. And then next, what you want to do is set up over here using your molar mass in a way that's going to allow you to cross out any units that you are not going to use and leave you with the one that you're trying to find. So if we know that 1 mole of water weighs 18 grams, we can set it up like this. It's 18.015 grams per, meaning divided by 1 mole. In other words, every 1 mole of water weighs about 18 grams. And as we talked about in class, the way that these little train tracks or these bridges work is you multiply across the top and then you divide by whatever's on the bottom. And you'll notice that when we divide by the bottom, the moles are going to cancel out, and that will leave us with grams. And if you'll recall from the prompt, we'll see that we're solving for mass, and we know that grams go with mass, so we know that we've done something right. We've set it up correctly. And so this, when we solve it, will give you 6.3 grams of water. This next problem, we'll switch it up a little bit. Instead of finding mass, let's try to solve for moles instead. How many moles are in 15 grams of aluminum? And then here on the right, you'll see I've got the block for aluminum. It has a molar mass of 26.982 grams per mole. And if you'd like to pause and try to solve this yourself, I would recommend trying that now. So I'm going to go ahead and set this up. As always, start with what we're given, which is 15.0 grams of aluminum. And I'm putting the moles of aluminum here on the end. Sometimes it's nice to set a target, like what are you working toward? And that can serve as a reminder. On these single step problems, it's not such a big deal, but sometimes we'll have problems that we have 4 or 5 steps in, and so having that target keeps us on track. So start with the 15 grams of aluminum, which is what we were given, and we know that 1 mole of aluminum weighs about 27 grams. So in this case, we want moles on top and grams on the bottom so that the grams will divide out or cancel out and leave us with moles on top. So you basically can take that molar mass and flip it upside down. Remember, it's always grams per 1 mole though. Don't put the grams with the mole. So 1 mole weighs 26.982 grams. And here, when we multiply across the top and divide by the bottom, you'll see that the grams divide out, leaving you with moles, which means we've set it up correctly. And then we would have about a half of a mole of aluminum. And you can spot check this. Does this make sense? Well, aluminum weighs almost 27 grams per mole, and then we said we had 15 grams of aluminum. So 15 grams is just over half of 27, and so it should make sense that our answer is just over 0.5. Let's keep going. Let's try a compound. So again, I'd encourage you to try this yourself. How many moles are in 0.0052 grams of carbon dioxide? You'll want to look at the periodic table. I recommend trying ptable.com, and you can pause here so you can try to solve it yourself. So in finding the molar mass for carbon dioxide, there's one carbon at 12 grams per mole. There are two oxygens at about 16 grams per mole, and the sum of this is about 44 grams per mole. So I'm going to need to use this number for my conversion factor. We'll always start off with what we're given, which is 0.0052 grams of carbon dioxide, and I like to put that target over there. I'm solving for moles of carbon dioxide. And then in this case, I'm going to put the molar mass of carbon dioxide on the bottom. Just like our last problem, we want to solve for moles this time. So we want the 1 mole on top and the grams on the bottom, so that our grams divide out. And then we multiply across the top. So 0.0052 times 1, and then divide it by 44.009. Now this gives me 0.00012 moles of carbon dioxide. But you're going to find that some of our numbers are incredibly small or incredibly large. And so sometimes we need to save the zeros, and we'll use something called scientific notation. And all you're doing, it's a very simple process, is you're moving your decimal to the right of the very first non-zero number. In this case, that's my 1, and it's a simple process. If I move this decimal, I would move it 1, 2, 3, 4 times, and so I'd say 1.2 times 10 to the 4, but notice that my original number is less than 1. And because it's less than 1, this exponent must be negative. If it were a positive, then that would mean I would have a number of 12000, which would be what, about 12,000. So those are very different numbers, so it's important to make sure that the exponent is negative if your original number is less than 1, or positive it's greater than 1. Let's try another one. What's the mass of 2.5 moles of hydrogen? Notice that this is a diatomic molecule, meaning it's made of 2 atoms. So hydrogen's molar mass, there are 2 hydrogens, times 1.008 grams per mole gives us a molar mass of 2.016 grams per mole. So we'll start off with what we were given, which is our moles, and our target is grams. So we're solving for grams of hydrogen. We're given moles of hydrogen. And you might, again, pause if you haven't already and figure out, how am I going to set this up? Do I want grams on top or at the bottom? And where should my moles be? Because we're solving for grams, we want those on top. So the 2.016 grams will go on the top and the 1 mole will go on the bottom. In this way, my moles will cancel out. Multiplying across the top and dividing by the bottom is really not necessary since it's just 1, but you can if you like. And you end up with grams of 5.04 grams of hydrogen. One more slide here. Now let's do some problems where we're actually using Avogadro's number. You'll recall that that's the number of atoms or molecules in 1 mole of a substance. And so for our intents and purposes, anytime you see a problem utilizing atoms or molecules or formula units, that's when we will be using Avogadro's number. So in this problem here, we're asked how many atoms are in 15 grams of aluminum. So we can't really go directly from grams to atoms. There is no direct conversion. So we need a couple of steps. So here, again, we're going to put our target down of atoms, and we have our starting point is 15 grams of aluminum. Well, we know that aluminum's molar mass, if we look that up, is 26.982 grams per mole. So that could get me to moles. And I know that according to Avogadro's number, there are 6.022 times 10 to the 23rd atoms per mole. So there again, we hear the mole. We can use that mole as our center point or our connection between the two types of units. And so that molar mass is going to be our way to go from grams all the way to atoms. So if you look at the periodic table, you'll find that the molar mass of aluminum is 26.982 grams per mole. And in this case, our grams would cancel out, leaving us with moles. And now from here, I can use Avogadro's number, because in 1 mole of any substance, no matter what it is, there would be 6.022 times 10 to the 23rd atoms. So 1 mole, in this case of aluminum, would contain 6.022 times 10 to the 23rd atoms. My moles would divide out, leaving me with atoms. And so I multiply across the top and divide by the bottom number, and I would get my final answer. Now, one note on your calculator, it's important that you don't actually type in times 10 and then have an exponent of 23. It gets you off by a little bit. Most calculators have a function called the EE function, and it works the best in terms of using that exponent. And the way you would type it in is 6.022. Then you would hit your EE button, type in 23, and that's how you enter in Avogadro's number. Let's take a look at one last example, and I would encourage you to pause and try to solve it yourself. The question is, what is the mass of 3.50 times 10 to the 22 atoms of iron? So in other words, we have this number of atoms of iron, 3.5 times 10 to the 22. How much does that weigh? So as always, we're going to throw down our target, which is not moles, it is iron. That's a typo. We'll have to fix that. That should be grams, rather. 3.5 times 10 to the 22 atoms of iron is what we are given. And 1 mole of iron would contain 6.022 times 10 to the 23rd atoms. Remember, 1 mole of anything has Avogadro's number of atoms in it. So the atoms would cancel out, and now we have moles of iron. And so from here, what we'd want to do is go from moles to grams, and we'd look at the periodic table, and we would look for the molar mass of iron, which is 55.845 grams. And so the moles would cancel out, leaving us with grams, and that would give us 3.25, not moles. This is a typo. I'll be fixing that. Grams of iron. And so notice that we multiply all the way across the top. The atoms cancel out, the moles cancel out, leaving us with grams. This will be grams as soon as I can edit the video, and that is how you use Avogadro's number. I hope that that was helpful.